Hi everyone, welcome back. In this lesson, we're going to be looking at in-class activity 12B or lesson 12B, working through college. So many undergraduate students are employed at the same time they're enrolled in school. In 2018, the National Center for Education Statistics reported that 43% of full-time students also worked. Being employed while in school can help pay tuition, housing, and other expenses, but it can also be associated either positively or negatively with the student's academic performance. So for question number one, they ask you to think through, do you think working while in school has an overall positive or negative association with an academic performance for full-time college students? And explain your answer. So go ahead and stop the video right now and pause it, and then just jot down for the next minute or so what your thoughts are. Okay, welcome back. For some people, you might have written down that it's a negative association because it takes time away from your classwork, spending time at night studying and so forth. Some of you might actually have said it was a positive, saying it gives you structure and so forth. So again, there's no right or wrong answer here. And we're going to hopefully look through data to kind of give us some indication of whether this is true or false. Okay. So objectives for this activity are going to be, you understand the t distribution. It's very similar to the normal distribution, as you're going to find out. It can be used to model the distribution of a standardized sample mean from a random sample when the sample standard deviation is substituted in for the population standard deviation. So again, this is when we don't know the population standard deviation and we have to use a substitute called the sample standard deviation. This leads us from away from a normal distribution to a t distribution. The t distribution is only valid as a model of the distribution of a standardized sample mean if the population distribution is normal to begin with, or if the sample size is large or large enough. You'll be able to calculate a t statistic given an observed data set, find probabilities involving a t statistic using the appropriate t distribution, and assess condition when a t distribution can be used. So a random sample of 15 employed full-time students at a large university was selected for a survey on employment. The following is the number of hours in increasing order work per week for each of those 15 students. And you can see they range anywhere from 2 hours up to 50 hours. So now it asks us to go to the Data Center Math Pathways Explore Quantitative Data Tool at this link. Again, you can either type this link in, hopefully you already have the DCMP data tools already bookmarked, or and then click on that link within there. So we're going to go to the Explore Quantitative Data. So let me switch over to the screen and share my screen for a second. So share screen, screen 2. Again, you can go to the DCMP, Data Center Mathematics Pathways Data Analysis Tools, and looking for exploring quantitative variables. And here's the link that was given to you in that lesson. If you click on this, it'll bring you to the exploring quantitative variables. We're going to do a single group. We're dealing with just a single set of data. On the lesson, in step 2, it asks you to select your own. It asks you to name it hours worked per week. And then it asks you to type in those 15 numbers. I'm going to cheat a little bit because I already have the lesson drawn up. And I'm just going to go ahead and highlight those 15 numbers and copy and then paste them in here just to save a little bit of time. And I'll turn all of the different plots that we want to look at. The histogram, the box plot, and the dot plot are over here. You can see here's the histogram, here's the box plot, and here's the dot plot. I'm going to copy these and put them into our lesson. You'll see them in just a second. You can see the mean is 21.6, standard deviation is 13, and the 5-number summary and the IQR over here. Sample size is 15. So let me switch back to our lesson now. Stop sharing. So you can see that I copied the histogram, the box plot, and the dot plot into our lesson. And now it says examine the histogram, your box plot and dot plot and summary statistic. Again, the summary statistics I didn't copy over. Write a few sentences describing the features of the data distribution. Address the shape, center, spread, and outliers. Okay, so go ahead and pause the video and write down what you think a description of these different graphs are illustrating to you. Okay, welcome back. So I might say something like the distribution looks like it's skewed to the right slightly. So the distribution is slightly skewed to the right. The center is around 25. If you look at the box plot, it's closer to 23. Dot plot closer to like 23 or 22. So the center of the data is around 25 hours per week. And we're talking about how many hours a week a student works. With a range from 2 to 50 and a standard deviation of 13 hours per week. And I got this 13 off the descriptive stats on the analysis tool pack. Okay. So let me just show you these numbers again on the screen in case you forgot. So let me share screen. So again, I've got the actual mean is 21, but looking at the histogram, it looks like to be 25-ish. The standard deviation is 13. The median is 22, min is 2, and the max is 50. Because now it asks us, what is the sample mean hours worked per week? So again, looking at the descriptive statistic and using the appropriate symbol, remember the symbol for sample mean is X bar. So X bar, for our average of our 15 students, the average hours worked per week for these 15 students is 21.6 hours. Okay, what is the sample standard deviation and what is the appropriate symbol for this? So remember the sample standard deviation is denoted S. And from the sample statistics on the screen, it was 13 hours. So a typical student in that sample of 15 students works 21.6 hours a week with a typical spread of 13 hours a week, typically 13 hours above or 13 hours below the 21.6. And that's how the average turned out to be 21.6. Okay, part D asks us to write a sentence interpreting the standard deviation in the context of the problem. So go ahead and pause the video and just write a sentence. Okay, welcome back. So again, the answer is going to vary based on the student's individual words, but the interpretation is something like I just mentioned before, the typical student works 21.6 hours per week and generally students work 13 hours from this mean. So again, 13 away would be 34.6, or 13 below would be 8.6. So generally, students are working 8.6 or 34.6 hours per week, and that's how the average turned out to be 21.6. Suppose the hours of work per week for all employed full-time students at this university varies according to approximate normal distribution with a mean mu and a standard deviation sigma. Consider the standardized sample mean. or the z-statistic. Remember to calculate your z-score for a single population with respect to the mean is x bar, the sample mean, minus the mean of x bar, which is the mean of the population, divided by the standard deviation of x bar, which, if we recall, the standard deviation of x bar is the population deviation over the square root of n. Population deviation is sigma, and n is your sample size. So now it asks us which of the following quantities in this formula are parameters and which one are statistics. Okay, generally, the symbols that are Greek letters or Greek letters of the alphabet are your population parameters, and the English letters are, generally speaking, your sample statistics. So in this case, there's 4 values here. X bar is a statistic. So this value is coming from your sample, and mu and sigma, these 2 symbols are your population parameters. These are parameters. And n, remember, just represents what sample size you're taking. So n is the sample size. It's neither a statistic or a parameter, just a value you choose to sample. Okay. If we were to take repeated random samples of size n from this population, n equal to 15, which of the quantities in the z-statistic could change from sample to sample? There may be more than one correct answer. So in this formula, x bar minus mu divided by sigma over square root of n, the only value that's going to change from sample to sample is your sample statistic, in this case, x bar. Your sample mean is going to vary, but your population mean and your population deviation are locked in. They're single values from the population, and little n doesn't change because we're saying we're repeatedly taking a sample size of 15. So the only value that changes is that x bar right there, that's sample mean. What distribution does the z-statistic follow across many random samples? Because we've standardized our values, the z-score and these values are now coming from a standard normal distribution. So what distribution does the z-statistic follow across many random samples? It follows, I should say, it follows a standard normal distribution. Recall, a standard normal distribution is when the mean is 0 and the standard deviation is 1. Okay, sometimes they abbreviate this like this: normal distribution 0, 1. In other words, the mean is 0 and the standard deviation is 1. So our z statistics will always follow, and z is a z-score. It's first represents a standardized sample mean. Always comes from a standard normal distribution where the mean is 0 and the standard deviation is 1. Okay, now it says, suppose we know the mean hours worked per week for all employed full-time students in the university is 19 hours, but we do not know the value of the population standard deviation sigma. If we want to calculate the value of a standardized sample mean, however, we need to know sigma. So instead of sigma, the next best thing to use is our sample standard deviation S. So this is the analogy I'll give you is sigma might be like sugar in somebody's coffee, and S is like Splenda. It's a substitute. So the real deal, the real value is whatever the population deviation is. But if you don't know that, we have to use the next best piece of information. In this case, to approximate population deviation, we're using the sample standard deviation S. But this is a substitute. Recall that an estimate of the standard deviation of the statistic is called the standard error of the statistic. Since we estimate the standard deviation of the sample mean, sigma over square root of n by substituting S for sigma, the standard error now is standard error of X bar, the standard error of our sample mean is S over square root of n. So again, we're using a substitute. Instead of sigma, we're using the sample standard deviation. And this is now going to lead us to what's called a t statistic. Because we're using a substitute, S in place of sigma, it's not a z distribution, it's a t distribution. So now consider t, and you're going to compute it basically the same way. X bar, the sample mean, minus the mean of X bar, which is your population mean, over the standard error of X bar, which now we're substituting in S in place of sigma, S over square root of n. So again, here's how we computed z. It looks like exactly the same formula, but here we knew the real value, the real deal, sigma, population deviation. But if you don't know this, if you know it, it's a z distribution. But if you don't know it, then you got to use the next best thing, the substitute, the sample standard deviation. And now this is referred to as a t statistic, not a z statistic. And you're going to see this t statistic, the t distribution, is very similar in many regards to the normal distribution, but because you're using a substitute, it's somewhat less reliable than the real deal. So part A, which of the following quantities in the t statistic are parameters and which ones are statistics? So in this case, mu is a parameter. So remember, mu is a Greek symbol. That's the population parameter for the mean. This is your population mean. But now X bar and S are your sample, come from the sample, they're sample statistics. So X bar and S are sample statistics. X bar is your sample mean and S is your sample standard deviation. Again, N just simply represents your sample size. So now if we were to take repeated random samples of size n equal 15 from this population, which of the quantities in the t statistic could change from sample to sample? There may be more than one correct answer. So now in this formula, the statistics that change from calculation to calculation, if you do it repeated many times, are your sample statistics, X bar and S, your sample mean and your sample standard deviation. So the answer down here would be A, your sample mean is going to vary from sample to sample. In C, S, your sample standard deviation is going to vary from sample to sample. Okay, so now it's going to ask us to go to the Data Center Mathematics Pathway T distribution tool. Again, to get to this, you can either type in the Shiny app URL, or either I'll go to the Clearinghouse Data Center Math Tools website and just select it. So under the Explorer tab, select and show standard normal curve. Compare the t distribution for 3, 8, and 14 degrees of freedom. We'll talk about what degrees of freedom mean in a little bit. Explain what happens to the t distribution curve as the degrees of freedom increases. So let's go ahead and do that right now. I'm going to share my screen. Okay, so again, here is our clearinghouse of all the apps you need for this course at the DCMP. Again, that's Data Center Mathematics Pathways Data Analysis Tools. So down below, you can look at exploratory data analysis. We just did the one for quantitative variables. Association, correlation, regression, we do bivariate data or multivariate data. And this is the one we want to look at now, distributions. You've seen the normal distribution in action up to this point. Now we're going to explore the t distribution. So if you click on the t distribution and you click on this link, which is the link that's in your lesson, it'll bring you to the t distribution app, which is going to be this guy right here. Let me just refresh it. And at the top, you can see there's tabs. The t distribution, explore, find probabilities, and find percentiles and quantiles. So it says to click on this show standard normal. The standard normal is the darker one. The t-distribution is the green one. So you can see the darker one is this guy right here. The t-distribution looks and smells just like a normal distribution, but you can notice the green has a little more area, a little more probability in both sides of the tail. It's symmetric. Okay, degrees of freedom. Again, we're going to talk about what that means a little bit later on. But it says, look at the degrees of freedom of 3. So in degrees of freedom of 3, notice, check out this little green area in the tail on the left side and the green area in the tail on the right side. It says, let's look at it for degrees of freedom of 8. Notice how that little area right there is getting smaller as we make the degrees of freedom bigger. And the overall t-distribution is getting closer and closer to a true normal distribution. And they say, look at it when it's 14. Now notice it's even closer to a true normal distribution. The green areas in this tail, the difference between the t-distribution and the darker normal distribution is getting smaller and smaller. So the t-distribution is approaching a normal distribution. Okay, so let me stop sharing for a second. Explain what happens to the t-distribution curve as the degrees of freedom increases. Okay, so I'll give you a minute to write down your thoughts based on what we just talked about, and you saw visually what was going on there. Go ahead and pause now. Okay, welcome back. So something along the lines as the degrees of freedom increases in a t-distribution, the t-distribution gets closer to a standard normal distribution. So as the degrees of freedom increases in a t-distribution, the t-distribution becomes closer to a standard normal curve, or standard normal distribution, standard normal curve or distribution. Other things you can mention is that there is one peak and it looks similar to a normal distribution. The t-distribution just has a little more probability in both sides, in either tail, on either side. Okay, so let's summarize. The t-distribution. When taking many, many random samples of size n from a population distribution with a mean of sigma, with a mean of mu and a standard deviation of sigma, the t statistic computed almost identical to the way you compute a z statistic. X bar, your sample mean minus your population mean over the standard error of X bar, which is in this case S over square root of n, not sigma over square root of n, because we're substituting S in place of sigma, will follow a t distribution with n minus 1 degrees of freedom. You're going to say, why n minus 1 degrees of freedom? That might become evident later on, but it has to do with theory of statistics. So for right now, just take it with a grain of salt, that this distribution, when you use a sample size of n for a single population, will have n minus 1 degrees of freedom. In other words, your sample size minus 1. If the population distribution is normal, so if your distribution you're starting with is normal, or the population is not too skewed, and again, your sample size is large enough for all practical purposes in our course is going to be greater than or equal to a sample size of 30. So again, the t statistic is computed very similar to the way you compute a z statistic. The only difference being that for the z statistic, for the standard normal, you're using a standard error of sigma over square root of n. But in those situations where you don't know sigma, and you got to use a substitute, we're going to use the substitute of S, which is your sample standard deviation. It now follows a t distribution with n minus 1 degrees of freedom. Okay, since the t statistic exhibits more sampling variation than the z statistics, its distribution has slightly more variability than a standard normal distribution. And that was evident when we looked at the visual that there's a little more probability in either tail, the left tail or right tail. However, as the sample size increases, there is less sample variability associated with the standard error of the sample mean. So its distribution gets closer and closer to a standard normal distribution. And in fact, in theory, if you could sample an infinite, if sample size was infinite, then the T becomes a Z distribution. But just take that with a grain of salt. There's less sampling variability with a standard error of the sample mean, so its distribution gets closer to a sample normal distribution. So the picture below shows various degrees of freedom along with the standard normal distribution for reference. So the standard normal is the solid one. T distribution with three degrees of freedom is this kind of big dotted one. You can see that the big dotted one has a little more probability in either tail. And as your degrees of freedom increases, there's less difference between the T distribution and the normal distribution. Okay, question 5. Assume the hours worked per week for all employed full-time students at this university varies according to an approximate normal distribution with a mean of 19 hours. So it's making that assumption that the initial population is approximately normal, so this applies. So remember, this formula will apply as long as the original population is normal to begin with, or if the population is not too skewed and we have a large enough sample size, at least 30. So this one's already assuming the original distribution, the original population was normal. Part A. Calculate the standard error of the sample mean for the observed sample data shown in question 2. Write a sentence interpreting this in the context of the problem. So if we go back to question 2, recall that this was for a sample of size 15. We had a sample mean of 21.6, and we had a sample standard deviation of 13. So remember that the standard error of X bar, so they refer to as SE of X bar, is S over square root of N. So in that problem back in question 2, we know that the sample standard deviation was 13, and we know that our sample size was 15. So 13 over the square root of 15, if you do that on your calculator, 13 divided by square root of 15 is 3.36 hours. So that's the standard error of your sample mean. Typical error. This is typically how far away your sample mean will be from the center, the true value. So now they say write a sentence interpreting this value in the context of the problem. I kind of just described that, but you could write something like, I estimate that the typical difference between the sample mean hours worked per week for a random sample of 15 employed. It's important you write out every possible detailed information so you don't miss anything. So for a random sample of 15 employed full-time students at this university, and a population mean of 19 is 3.6 hours. Again, there's other words you could use, but 3.36, sorry about that, 3.36. So there's other words you could use, but again, basically what you're saying is that your typical spread of X bar is typically 3.36 hours away from the middle. So now it says, calculate the value of the T statistic for the observed sample data shown before in question 2. write a sentence interpreting this value in the context of the problem. So again, we're assuming the population mean was 19. And if we recall back from 2B, we had a sample mean of 21.6. So for this particular sample of 15 students, if you recall, these 15 values right here had a mean of 21.6 hours. Assuming it's coming from a population with a mean of 19, then our T statistic or T score, remember, is X bar minus the population mean over S over square root of N, which is now we're using as our standard error of X bar. So our sample mean for those 15 students was 21.6 hours minus what we assumed the true mean was from the entire population 19 over our sample standard deviation over square root of N. This is just this guy copied. So if you did 13 over square root of 15, you'd still get 3.36. So again, that's your, got to be very careful how you type this in your calculator. You got to parenthesize. You got to make sure that subtraction is first, that square root and that division are then second, and then that guy is third. So you can parenthesize to make sure these guys are done in the right order. So if you do this on like a TI calculator, you could type in parentheses, the numerator 21.6 minus 19 divided by parentheses, you type in the whole thing, 13 divided by the square root of 15. And that gives you 0.7745. To 2 decimal places, this is approximately 0.77. Okay, it wants to interpret that. So remember, since this is positive, our sample mean was above the mean, the population mean, and it was 0.77 deviations above the mean. So you could write something to that effect. So the observed sample mean hours worked per week of 21.6 hours is 0.77 standard errors above the population mean. Standard errors, remember a standard error is 3.36 hours above the population mean of 19. So again, this is just a relative standing. 21.6 hours, what we got from our sample, is 2.6 hours above the mean, the population mean, but in the context of what a standard error is, it's 0.77 typical errors above the mean. Okay, so now question 6. Consider the T statistic for question 5B. This guy right here. What distribution did the T statistic come from? Explain why the condition for the T distribution are met, and then draw a sketch of the distribution. Okay, so first of all, let's explain the condition. The condition is met because the original distribution we observed was somewhat normal. So why is the condition met? Condition was met because we were informed that the original distribution was normal to begin with. Condition was met because the original population distribution was normal. Remember, there's two conditions. Either the original distribution could be normal, your population or parent distribution is normal, then we're okay, or it's not too skewed and we sample at least 30. And remember, at least 30 is considered to be a large enough sample size. Okay, what's the distribution? Because this was met, then we have a T distribution. And because our sample size was 15, we have 15 minus 1 or 14 degrees of freedom. So the distribution is a t distribution with n minus 1, or in this case 15 minus 1, or 14 degrees of freedom. Say degrees of freedom. And this is what the distribution looks like. It's just a rough sketch. Again, it looks and smells like a normal distribution or standard normal, but this one would have a little bit more probabilities in the tail. We had talked about that already. So here's a sketch. Okay, part B. The probability of observing 0.7 or higher in the standard normal distribution is 0.2206 or 22.06%. Would you predict the probability of observing 0.77 or higher on the distribution you just specified in part A to be less, equal, or larger than 22.06? Remember, in the normal distribution, here's 0.07 right about here. This area right here was 0.2206. But under the t distribution with 14 degrees of freedom, we're picking up a little more area. So we'd expect that probability to be a little bit bigger than 0.2206. So it's going to be bigger than 0.2206. So you'd expect it to be larger because the t distribution has a little more area, which is synonymous with probability, in its tail than a standard normal. Distribution. Using the find probability tab in the Dana Center's Math Pathways t distribution tool, calculate the probability of observing a t statistic of 0.77 or higher for the distribution you specified in part A. Again, that's a t distribution with 14 degrees of freedom. Does this match your prediction from part B? So again, we're thinking it's going to be a little bit larger than 2206. So let me go to our screen. And here's our t distribution. I got to refresh it. And since we want to find the probability, we're going to find probability. And we have to set this to 14 degrees of freedom. And we want to find the probability of being larger than 0.77, which is right here. So we want to go upper tail. I want that upper tail probability. And we want to be larger than the value we just obtained, 0.77. So you can see this darkened area right here for the t distribution with 14 degrees of freedom, upper tail bigger than 0.77 is 22.7%. If I went back and did the normal distribution, just to refresh your memory, if we went back and did normal distribution and open up that app, and I apologize, I should have had it open earlier because it does take a little bit of time. So just wait patiently for it to open. You'll see where the 2206 comes from. So if we have a standard find probability, if we have a standard normal distribution with a mean of 0 and a standard deviation of 1, and I say I want to find the upper tail where it's 0.77, you see that's where the 2206 comes from. That's the area, the probability that you get a z-score bigger than 0.77 under a standard normal distribution. Again, ours was a t distribution with 14 degrees of freedom because our sample size was 15. 15 minus 1 is 14. And to get a value above 0.77 is 22.7%, which is just a little bit larger than the 2206. Let me stop sharing for a second. So in this case, use the find the probability tab, calculate the probability. So the probability is 0.2270, which is 22.7 versus 0.2206 or 22.06%. So does it match our prediction? Yes. This value right here at 22.7% is slightly larger than the 22.06%. So again, in a T distribution, the probability of going further out in the tail is going to be slightly larger than in a standard normal distribution. Okay, I hope this concludes the lesson. And if you have any questions, please make sure you contact your instructor, and we'll see you next time. All right, take care. Have a good day.